module, actually, you have gained some better insights, integration, and will also help you in your career or in your future pursuits, whether it's research or other type of careers that we'll be doing including materials, analysis, and characterization. Okay, can I have a show of hands? How many of you have decided to join the semiconductor industry or receive an offer? Decided or, receive an offer? Okay. Okay. And how many of you will be in graduate studies? As well. Both in industry and academic and graduate studies. Okay.
That's how
Yeah, if you are pursuing a PhD or a master's, right, that's considered graduate studies. But in fact, there is such a pathway that engineers in the company can return to school to pursue a PhD, and it's sponsored by EDB, Economic Development Board. So you still have your position in the company, but you will receive the salary to do your PhD instead. IPP. That's called IPP. Okay? No, it's not. It's not difficult.
Maybe like you do
no, company will relieve you of the workload. Yeah, because the budget actually comes from EDB. So the company will be very happy. They get a big count, and yet the salary comes from EDB. So this is what your government is doing for you. Okay, please take good advantage of it. Okay. All right. So now let's start. Just a quick refresher, right? We have been studying at this point how to build a planar transistor, in which this layer is the oxide, which is the key, the heart of a transistor. How well a transistor performs, surprisingly, really depends a lot. This whole front end process where you have the gate, which is a metal light, and then oxide and semiconductor. That is what we call MOS. Very often you see this MOS. Right? CMOS means complementary. You have a P, you have an N next to each other. So for this gate step over here, like we say, right, traditionally this has been SiO2, right? So in this case, why do we want to change to high K, and what do you think would be the issue? So why, right, and the issue. So when you look at the question, just catch the keywords so that you can answer accordingly, or else you'll be confused, about what's it asking. Okay, so why, right? High K is needed. So maybe any one of you want to volunteer quickly just to give me some keywords as well?
higher transistor performance.
Right, transistor performance. Remember, we say that if you change to high K, right? By the way, why? Better transistor performance.
Lower BG easier to turn on.
High K.
For the same thickness, we can have high performance.
Correct. Correct. You can actually enlarge the process window, right? For the same thickness, right? You can actually have a higher capacitance, right? That's one way to understand it, right? Or, right, with that you can actually scale down further. Okay. So when you explain, right, try to explain the concepts that you have assimilated. For example, here it's just some also keywords, right? But you can elaborate it to make it, more understandable, right? It helps to reduce the effective oxide thickness. That means it's equivalent to an SiO2 that is thinner, right? Because of the performance. The equivalent oxide capacitance, right? The equivalent oxide capacitance is actually higher, and to reduce heat leakage because physically it is thicker. Right? Physically it can be thicker. To achieve the same performance, you can have a thicker material, right? That's the idea of it. And to allow further scaling, because it's thicker now, right, I can buy more time, buy more generation of technology nodes to scale down, right? It allows further scaling down to achieve a better performance. So integration issue, we know that it's always not easy. One of the key challenge is the interfacial oxide, the roughness, right? These two you're probably quite familiar. It's covered in the lecture. We discussed why, the interfacial oxide thickness. Let's say if you have another layer that is in between, where this capacitance, right, is already one capacitance here, another capacitance here. So they are arranged in this case, right? Your C total will be 1 over C1 plus 1 over C2, right? If C2 is low, right, you can imagine, right, if this is low, this whole picture becomes bigger, it will dominate your C total, right? That is why we try to eliminate such parasitic layer, right, that doesn't help in the total capacitance. Okay, so which is the reason why we want to avoid any interfacial oxide. Interface roughness, right? What would be the issue? Why do you think if there's roughness, there will be any problem? Yeah, so you have potentially some thinner region and some thicker region, right? If it is rough, right? So what would that affect? Correct, because the current, right, might then be prone, when you apply a potential, for example, the field, electric field. Electric field means the voltage divided by thickness. That's called field, right? So the electric field at the thinner layer, right, would then be higher, right? So it might also cause the breakdown at the thinner region. Okay, so that's how you understand the impact of the words, not just the words is important, but the meaning behind it and the consequences, right? Try to understand why so. And then there is this concern about edge stop due to silicon loss. Is when you try to pattern this gate, right? Because it doesn't pop up to be like that. You don't deposit the oxide just here, deposit the metal here. When you deposit, it's everywhere, right? It's a blanket deposition, right? It's not selective, it's everywhere, blanket deposition. How do we end up with this? You do patterning, right? Lithography. So during lithography patterning, right, there will be etching, right, removal of the areas that are empty here, right? So during the removal, this oxide remover, right, the etch process needs to be very well tailored. Else, right, what happens is that it will cause the loss at the substrate. You cannot stop. The etch stop is not so obvious for metal oxide. So the etch selectivity, right, is quite challenging, and patterning of the gate stack would become an issue. So this etch stop, due to silicon loss, is referring to patterning of the gate that might, when you try to remove, that may be too fast, right? Then it can't stop well at this metal oxide. Then it will eat into your silicon substrate, leads to a loss in the substrate material, right? So this is also undesirable. And when you select the high K, right, we also need to consider work function compatibility. Okay, this work function is not just, it's not for the high K, it's the metal gate. So when you select already a high K material, you have to adjust your work function of the gate. Okay, because usually in a Venn diagram, right, what you see is that SiO2, the gap is actually very large because it's insulated, right? Maybe the gap is about 9 electron volt or something. Then you have like this, right? So this is metal, where you have work function. So this work function, when you have fixed this, the work function selection must be hopefully within the gap, right? You cannot select an oxide that is too small, or you don't have a choice of a metal gate laser that is always too high here. Okay, so ideally is to contain this within here so that you have a wide range of semiconductor doping concentration that you can map to. So it's a full package selection actually. So when you change one, right, it may tend to change another that cause the problem in, for example, band bending and therefore threshold voltage adjustment. So in earlier days when we can't change the metal gate, we use threshold voltage implantation to adjust. We implant into the polysilicon. So that's why you have heavily doped polysilicon as the metal gate. Okay, so that's the reason why we heavily dope this polysilicon. Right, so it's always heavily doped so that it's having a property that's similar to a certain work function to adjust the so-called work function of the metal. Okay, so that's where we come this angle come from. And any other issues that you might foresee? Any thoughts?
So can you explain the work function compatibility?
The work function compatibility, right? Meaning, let's say, okay, you decided not to change the polysilicon, right? Then when you select the oxide, you have to make sure the band gap is large enough. So for SiO2, the band gap is pretty large, but you realize that when you choose aluminum oxide or hafnium oxide, the band gap tend to reduce. So when it reduces, right, you need to check whether this level is it still not so close to the conduction band gap. There must be sufficient offset.
So basically the semiconductor band gap must be larger than the metal oxide.
The oxide has to be bigger
The
gap.
oxide has to be
Yeah, bigger gap. Yeah. So that this band edge is sufficiently wide. This is the band edge offset that we do not want easily, the current to go through.
Okay, because you want to hide to inhibit.
So to inhibit any leakage as well. Okay. Any other issues that you might have foreseen? Right, thermal stability is another key concern. Yeah, that's correct, because very often we find that when you increase the temperature, any metal oxide, let's say hafnium, SiO2, there is a tendency to take in some silicon. It becomes like hafnium SiON with SiOX. Then because of this, we start to anneal it in nitrogen to stabilize it, to form SiON. Because nitride is also a good oxide, a good dielectric, a good insulator. So we do nitridation to passivate any deficiency in oxygen. Okay, so that's one way to overcome this issue. So that's related to thermal budget issue where it leads to non-stoichiometry in composition. Right, when you increase the temperature, the formation of hafnium oxide or the hafnium oxide may interact with other materials. Okay, so this second question, right, is actually related to electrical capacitance measurement. Okay, let's say an engineer, right, he did a high frequency measurement, right, high frequency voltage measurement. If you want, you can come to my lab, I can also show you how to do the measurement. Okay, so we have a P substrate that is a MOS structure, right, it's a test structure. You press the button, then you collect the high frequency capacitance. Then there's some trend in the line, right, that comes out, capacitance versus voltage. Okay, then you realize this capacitance as a function of gate voltage, right, actually show this expression. It can fit into this analytical model that is 6 plus 12 divided by 1 plus exponential gate voltage. Okay, so then the question is, how do we then from this line, the trend, right, calculate the oxide capacitance per unit area and the oxide thickness? The test structure, right, the device that you are testing, actually you know that the area you can measure, the pad size area is actually 100 by 100 micrometers square. Of course, it's fairly small, your eyes can't see it. There will be a probe, there will be a microscope with a probe. You look under my microscope, you put the probe there, then you press the button. That's how it is done. Okay, because it's a regular oxide material, so the relative dielectric constant is 3.9. So it's SiO2 material. So then I want to know, right, what is the oxide thickness? How thick is this SiO2? Okay, so how do you approach that?
Calculate capacitance.
Calculate capacitance, that's why I asked you to calculate the capacitance. So it's quite teaching you step by step actually. Yeah. So how do you calculate the capacitance is the question, right? Because we know that T anyway is from the capacitance, C ox equals epsilon A over T, right? So if you know C, you would know what's T. So how do we get the C?
This Vg is 10 towards negative under accumulation condition.
Okay, yeah, good point. So you're saying that from the measurement, right? So this is Vg, right? Or gate voltage, and this is capacitance. So this is a P substrate, right? Typically, ideal case, right? What kind of CV you would see? Let's say before you measure, it's always good to imagine what data you get. Else, you never know is it connection issue or what issue. So you imagine first, right? Based on your knowledge, what kind of CV behavior, ideal case, right, that you will see. Correct. Yeah, it's like the U or V shape, right? So you have some high value, then it turns down, right? And high frequency, it will go up, right? So how much it goes up, of course, depending on the frequency applied and so on. And here, when it is a P substrate at the negative region, this is a P substrate, you apply a negative, so what happens is the holes will get attracted to the negative, so you have this what we call P sub P, all the holes get accumulated, right? So because it's P sub, so all the positive charge gets stuck here, so it's accumulated. And this is negative Vg, so here, negative Vg, so we have accumulation. That means all the charges gets accumulated, so we have high capacitance. More charges, more C, right? Then as you go more and more positive, right, I sweep the bias from negative to positive. This negative, this positive. So as I go more and more positive, what happens here? So I go to more positive. So what will happen here? Yeah. So here, it will slowly, because positive now, right, you would have more and more charges. The positive starts to disappear, right? Disappear, so it drops. Right? So the charge drop. Then the channel gets inverted now. Right? It gets inverted because P substrate, my channel gets inverted with electrons. So because these are charges as well, so it rises. Okay? So that's how you get the U shape or V shape.
Sorry, this is for low frequency, right?
This is provided it is low frequency, slow enough that it gets accumulated. If it is very high frequency, then because they are minority carried in a P sub, right, then it's not fast enough, then you cannot track them, then it will drop. Because they are minority carriers, it's quite slow, so you need a relatively, frequency performance. Okay, so that's how you get this accumulation. Here, it starts to deplete, right? Drop, right? Deplete. So it's depletion. And it starts to invert, right? I told you it's inverted the channel, so it's inversion. So you have three regions. Okay. Okay, so here you have capacitance as the axis, right? This engineer who has measured it probably gets, let's say, the dash line or high frequency, something like that. So he get the solid line actually, right? Because high frequency. So in this case, how do we read? How do we get, what is the capacitance? In a way that is under the ideal case per unit area. So obviously, you should read the theoretical value. That means what is the best capacitance that you can obtain, the highest, right? So you can see that this point is here. What you measure is the solid line. See, it's a high frequency measurement. So it's here, right? So this region can be considered as the best optimum highest capacitance that the oxide can gather. So therefore, this is happening at Vg that is very negative. Correct? So you fit into the equation Vg that is very negative. So because it's a model, right? So we don't know what voltage. So you just give a very negative means, let's say you plug in a minus infinity. Okay? So you plug in a minus infinity, this term will actually disappear. Exponential, right? So at the end you get the theoretical highest capacitance, right? 18, yeah, very good. So then with the area, you can calculate already. Okay? Yeah. Okay, so please calculate and see whether is it correct. It's a theoretical model, so the oxide thickness will be a bit large. The number here is too high micron, so it wouldn't be like that actually, right? That means this expression probably needs to be tailored to derive a better oxide thickness. Okay. So now the question is quite helpful because it is telling you it's a high frequency measurement. If it is a low frequency measurement, right, you might follow the dash line, right? Then you have a choice of using this high value or this point, right? So you would have to decide whether do you choose this or this. So what do you think? So if the question is low frequency, right, you will get this dash line. So you have this is the C max at accumulation. You might have another C max here, let's say, at inversion.
Depends on the application. Depends on why you have application. Because if you use it MOSFET, you'll be operating on the accumulation side anyways. So you'll be more logical to pick that side.
For the BJT side, you want the minority carrier, so you will select from the inversion side.
Right, yeah. Inversion actually is very useful. Many transistors are operated under inversion, actually. When you have a turn-on voltage, you're using a minority carrier. However, in the typical logic transistor, the C inversion here, this side, is affected by a lot of defects. A lot of defects. For example, one example, right, is the issue that I've introduced that's called polydepletion. Right? So you actually see that this inversion might fluctuate up, down, depending on how your neighbor is performing. So not only itself, your neighbor as in the polysilicon. right? So that is why the safest approach is still taking this part. It's not affected by the C depletion. Okay, this is just for your understanding as well. Any questions? Okay.
Yeah, Prof. Your exam has to be wrong.
Huh?
Because using nanometers instead of micrometers.
90 nanometer, huh? Nanometer, you sure?
I think so.
Okay, then that is more correct. Because I would expect it to be nanometer. That's why I see it why micrometer. Yeah, because oxide should be thinner. Okay? Yeah, nanometer will be. Yeah. Thanks. Check, huh? That's why I look at this answer a bit strange. Maybe it's question 2. Choose a high K material for this from this table, right? I need to speed up a bit. What we want, right, is to select something that has 6 times the thickness, 6 times thicker to achieve the equivalent oxide thickness, meaning that initially I may have X, right? My initial layer thickness could be X. So right now I change to a high K, right? I want this to be 6X, the thickness, right? So this is SiO2. But the performance, the C is still the same. Okay, so the capacitance, right, I want it to be equated. Okay, so you just equate the capacitance from both sides. You can try by plugging in everything, everyone, if you want, right, and then select accordingly. But it's quite straightforward here, right, because 6 times that of SiO2, right? SiO2 is how much? Yeah, 3.9, right? So it's quite easy to recognize that in this case, 6 times you would fit in easily for pumping oxide. Okay, so if I decided, right, that this X is unknown, right now I'm saying that this high K material, if 10 nanometer is being used, right, 10 nanometer, what is the equivalent SiO2 for this capacitance that can be achieved here? Right? What should be the SiO2 thickness be? Do you think it's higher or lower? Lower, right? So that is why we gain, right? Because physically this is larger, right? Where actually in SiO2 you need much thinner to achieve the same performance. So the advantage of high K, right? The purpose is therefore here. Okay. So similarly, you can equate the equivalent oxide thickness, plug in the information, you get that it's much lower. It's just 1.6 nanometer. Okay, so very small thickness of SiO2. So this is a realistic calculation. You can see that hafnium oxide, you can gain almost 10 times from here, right? 1.6 and now this 10 nanometer. Third question, what is the commonly adopted method, right, to deposit high K? Then describe the process and advantage and why PVD cannot use. So this is also, I repeated several times, right, the importance of ALD, right, for the implementation of high K. Actually, high K material, you can easily deposit using any equipment in the lab as well. You can use evaporator, you can use sputtering, you can use whatever, even chemical solution bath. If you give me 1 beaker and 1 or 2 powder, I can also deposit high K. Right? I also have a laser that I can, irradiate the laser to a target and deposit high K. Right? But all these methods, seriously, doesn't give a pinhole-free and defect-free kind of thin oxide. So, and plus the manufacturing line is now 12-inch per wafer. Right? This 12-inch wafer bigger than your face, right? So it's really very difficult to have a very uniform coating. That is why, right, ALD came into place, and it has the advantage of uniformity, conformality, and what? Sorry? Yeah, control thickness, right? So it's a layer by layer. Okay. So the key words, right, is the layer by layer coating. Self-limiting. Yeah, self-limiting or self-limiting surface. But disadvantage is slow, okay, conformal. So these are the keywords.
What is self-limiting?
Self-limiting, that means you have a precursor A coming in that's get absorbed on the surface. There are many other precursors in the air, right? But I purge it out. The purging step remove anything in the air. So when B comes in, right, the B cannot react with anything in the air. So it can only react with this layer. So it's self-limiting. It's not enough A to react with B actually.
Selective.
Hmm?
So it's like selective.
Yes. Yeah. So it will only react to those that are available already on the surface. So it's called self-limiting. So why PVD cannot be used? Actually can, right? I told you. PVD can deposit. Evaporator is a good method. Sputtering is a good method. If you Google, right, there are many researchers use these methods to evaluate high-K candidates. But in manufacturing, right, it cannot. So why?
Not as conformal, line of sight opposition.
Correct. So you have this line of sight issue that it's not conformal, and the growth rate is very fast as well, most of the time, that cause defects and therefore need image. Okay, so all these words you have it in your notes, so I'm not going to repeat line by line. Okay. So this question, right, is like you receive a sample that looks like that, right? So someone passes you this, in let's say you're working in as an engineer, then they tell you to continue with the process. So what would be the next step here?
Dialectic first.
Correct. Don't immediately jump into adding the gate. You will cause a lot of yield loss because there's no dielectric. Remember to have a dielectric first, then the gate. Okay, so this is the typical replacement gate process, where the dummy gate has been removed. Right? Remember we said this is pretty strange that you remove the dummy gate, right, and then you add the dielectric and the metal gate. Okay, so the purpose, right, of course, is to create a metal gate, right? That's the purpose. And the challenges. What do you think are the challenges here?
conformity.
So you're worried about the filling in of the gate because it's a trench, right? Yeah. The filling in is actually challenging sometimes if you are not able to fill in well. That is also one challenge for the replacement gate, right? And when you fill in, right, with the metal gate, we say that the metal gate can be using methods such as PVD because they're metal, right? So it can be everywhere. At the end, you need to polish as well, right? So finding a good polishing step for this metal gate is important for the success of replacement gate. So metal gate created the future process flow, right? So why is it required? We have discussed about the needs of this. Particularly, right, I want to emphasize the issue of poly depletion because this could be some challenge. So poly depletion, right, it happens when poly depletion happens. Actually, it's always there when you use polysilicon as the metal gate, as the gate. But as the device gets smaller, right, it becomes more prominent, right, because the gate oxide right now is there, the C-ox is actually higher, right? So as a result, your poly depletion, again, you have the poly depletion C1 and C2. This is C poly depletion. This is C oxide, right? Again, 1 over C total. So when this die gets small, really, this term will become dominating, right? So it would affect the C capacitance poly depletion effect here. That affects eventually everything might be governed by the poly depletion capacitance.
Actually, C-ox will increase with decreasing size.
C-ox would increase, yes. It will increase, so the whole term will become smaller, right? So this will be dominant. Is that correct?
Yeah.
So please consider this poly depletion issue, right, as it scales down. And a metal gate, right, also helps to reduce the RC because the resistance here for metal is small, right? Metal, the R is definitely small, right? So it helps to eliminate or reduce any RC limit. And boron penetration is actually happening when you dope the polysilicon. This polysilicon, let's say, is a P plus poly, right? Then you usually dope with boron. And this boron is quite light. It will go into the oxide very often. So we call that boron penetration. So when the oxide gets this boron, it will lead to defects. Okay, so that is why we want to overcome this issue. Even though poly depletion by right can be compensated using ion implantation. But when it's too high, you get this issue.
Question, can phosphorus penetrate as well? Because phosphorus
is bigger actually, so the penetration issue is not so high, not so severe. Boron is the one that's very susceptible. Okay, and also of course when you do metal gates, you can select different function. Okay, that's something for you to consider. Okay, so please look at this. You have the figure as well. So I mentioned just now the last step on the polishing, right? It's quite challenging as well. This step you have to consider, how to do a good polishing step. You know what's the issue of CMP, right? Did you learn earlier? Okay, good. Huh? Can connect now. Can connect with what you learned earlier on CMP.
Trying to go.
Try to
看到就是爸爸这样子的情况。
Okay. Draw a trigate and illustrate the benefit. So what kind of trigate is non-planar? It's non-planar, right? So I've drawn earlier many times the planar, right? So non-planar, how do we do it? Any volunteer? Come, sure.
Draw the picture.
Come, volunteer.
You know like that, tut1.
I never try. What's the impression? Doesn't matter. It's just impression. Impressionist, right? You know art.
Okay, let's try.
In art, there's a so-called impressionist.
So this is my M. M-O-S.
Wow.
Now the game come from here, here, 3-dimensional, try it.
So wait. I think you can patent this structure now. So the oxide grow vertical, huh?
Outside at the side.
How do you grow oxide pillar? The ALD cannot grow pillar. Try again. Maybe you can patent that. Samsung will come after you.
See, my third is the outside is the secret. My third is
So only the metal grow up now. Only the metal grows up.
yes, yes.
Anyone wants to modify this?
I think it's good enough.
But if I look at this, right, it is still like polysilicon like that, except race or strain, right? No, not the strain, it doesn't even raise. It's just a pattern metal. Yeah, so it's just a polymer metal, right? A mushroom metal, that's all. So, anyone who wants to modify this? Come, second table, any rep?
So here we are so
You.
Come, ladies.
She just drew a whole other one.
No.
So you can modify.
You can modify.
Give up. Spread.
Oh, 3D 想法。
哇
I draw the
Oh.